Assalamu alaikum. The topic which I am going to discuss today is the design of the steel beams. Well, a beam is usually considered as a tension member which is subjected to a transverse gravity loading or the vertical load. So any member which is carrying a load in the transverse directional or in the direction of the gravity is termed as the beam, whether it is the concrete structure or in the steel structures. So if we say that these are the beams or the horizontal members that are basically transferring the or taking the gravity load of the structures. Moreover, you can see these beams in the form of girders on the road bridges as well as similarly you could have the girders which are the most important beams, and then we have the stringers. These are the longitudinal bridge beams. They are the beams in the case of bridges which are longitudinal, and they usually span between the floor beams, and the floor beams are basically the major beams that supports the joist or the transverse beams in our structures. So if we have see our bridge structure, this is the girder which is the outermost part, and then we have a stringer which is in the longitudinal direction, and then we have our floor beams. If we see a cutout section or upper part, you can say that the girder is the outermost beam which is carrying the main load, and then the beam which are transferring the loads from the stringers towards the girders are called as the floor beams. And we have the stringers that are usually placed between the various floor beams. Like in this case, we have one floor beam at this end of the member and the other floor beam in the middle of the structure. So these two are called as floor beams. Joist. What is the joist? Joist is basically a beam which is supporting the floor construction. It is basically support the loads of the construction of any particular floor, but they are usually not considered as the major beams. Then we have the purlins. Purlins are the roof beams that spans between the trusses. So these beams that are spanning between the trusses, they are called as the purlins, or they are usually placed on the roof beams. Then we have a gears beam. Gears beams are the beam which are usually provided in the structures that prevents the wind loadings on either side of the building, and they are usually horizontal wall beams, while the lintels are the members that are supporting the wall load either over a window or over a door opening or any opening that is the load of any opening which is supporting the wall load is called as the lintels. Coming towards the sections that can be used for the beams, there are the many sections that can be used for the beams just like the columns. The most prominent of the section that is used in case of a beam is called as the W-shaped sections or wide flange sections, because they are proved to be the most economical beam sections, and they have mostly replaced the channel sections and the slope sections for using as a beam. Mostly in today's steel structures, you will see the beams in the shape of I section or of the wide flange sections. Moreover, sometimes we do use the channels when we have a very light loads in the structures, and these light loads are usually in the form of the purlins and the places or at the areas where we have a clearance available is very small, or we have a less spacing is over there. So less spacing means less loadings, and less loadings leads towards the use of these channel sections. This is the one of the typical example of a W section or wide angle sections. Basically, all our girders are the wide flange sections, or they are also called as the W shape or I section girders. The basic difference between girder and the beam is that the girders usually carry the much higher load as compared to the beams, and they are usually used in the bridges. Now, coming towards the designing aspect of the beams, we have the two theories or the two design approaches. One is based on the elastic design, and other is based on the plastic design. In the previous years, mostly the design of the steel structures and the analysis of the steel structures is based on the elastic design or the elastic theory. And this theory is based on the yield stress of a steel. But nowadays, this theory is replaced with another theory called as ultimate stress design theory, or the load and resistance factor design theory. Because this new theory is based on the plastic capacity of a steel structures, and this theory it proves to be the more rational and the more realistic theory as compared to the elastic design theory. In the elastic design, we assume that the maximum load that the structure could support is equal to the load that causes a stress somewhere which is equal to the yield stress of the materials. And then these members were designed using the bending loads such that for the service loading does not exceed the yield stress of the member divided by the factor of safety. And factor of safety in case of plastic design ranges from 1 to 2 or 1.5 to 2, while the other theory that we have is the ultimate design theory. If we look at the stress strain curve of the steel, the elastic design theory is based on basically till the yield point of the steel. And once the necking is produced in the steel, then we have the strain hardening stage. So this is the yield point where we have Hooke's law is followed. This is the range where the elastic design theory is used. But the recent research states that the steel members or the ductile members do not fail at the yield stress, but instead they keep on carrying the load till the ultimate stress. So the scientists are looking towards the using the area of these hard strain hardening stage as well. So the theory which uses this area as well is called as ultimate design theory. Moreover, in case of elastic design theory or the allowable stress design theory, one factor of safety is used that caters the entire uncertainty in the load and the strength. While in case of load and resistance factor design theory, which is usually based on the probability of the occurrence of the load, it uses different partial safety factors for different type of load and for different types of the strength of the beams. Like for tension, it has a different factor of safety. For compression, it has a different factor of safety. Similarly, for tension control materials, it has a different factor of safety, and for compression control region, it has uses the different factor of safety. That's why this theory basically supersedes the theory of the allowable strength design. Moreover, if we go in the story, we say that the engineering structures are used or by designed by using the theory of the allowable stress design theory, or called it as the elastic design theory, with the satisfactory results for many years. However, with the advancement in the research and with the development of the new materials and with the broadening of the knowledge scales, now the engineers become aware that the ductile materials like steel, they do not fail at the yielding stage, but they keep on taking the stress even after the yielding. So what does this mean? This means that such members have a much more margin of the safety against the collapse of a structure than the elastic theory suggested. So that's why the design is more shifted from elastic design approach to ultimate design approach. Now, coming towards the behavior of the beams, in case of the beams, if we consider the very basic concept that at the top of the beam we have a compression, and at the bottom of the beam of any cross section we have a tension from below the neutral axis. And if we draw the stress or the strain diagram of a material, it varies linearly from neutral axis towards the both extreme fibers, both towards the compression fibers and towards the tension fibers. And as we increase the value of the moment, it is also going to be increase in the yield stress of the material as well, till the material gets filled. So when this movement it goes or reaches beyond the yield stress of the material on the outermost fiber, it is going to collapse the material or going to separate the portion of the beam, and this process continues with more and more parts of the beam spreading, separating one by one from the cross section until a full plastic distribution is noted in the beams. The plastic distribution is basically the distribution in which there is no linear connection between the trans compression force and the tension force of a member. And we call this stage as the stage when the plastic moment is generated in the structures. And if we see the plastic moment initially the yielding and occur with the point of the loading, let's call it as the load pi. And once the yielding is starts, it is going to cause the stresses on the both fibers, tension fibers and the compression fibers. And as with the passage of time or with the increase in the stress, the two zones gets joined each other, the compression and the tension. Once these zones join with each other, it ultimately leads towards the failure of the member, and we call this as plastic movement failure, because we have seen the superposition of the yielding of two zones, one compression zone and the tension zones. So the progression or the movement or the linear expansion of the yield zone ultimately leads towards the collapse. And this collapse is basically due to the formation of the full plastic hinge in the member. And due to this plastic hinge, the yield zones spread over the entire cross sections. But what is the plastic moment? The plastic moment is defined as the moment that produces full plasticity in the member cross sections, and it creates a plastic hinge in the member. So, as the name suggests, plastic moment, it is going to induce a plasticity in the member, and which ultimately leads towards the formation of the plastic hinge. This plastic hinge, basically due to this plastic hinge, all the forces or the stresses are going to be concentrated at one section only. But it should also be noted that this effect could also be extended for some distance along the beam on the both side of the plastic hinge formation point. Other terminology that we used while the bending of the behaviors or the design of the theory is the plastic modulus. This plastic modulus is basically the resisting moment that is generated by the beam or by the material of the beam when the full plasticity is developed in the structures. So this resisting movements that resist the full plasticity generated in the member is called as the plastic moment, and we denote it with MP. And this plastic moment is numerically equals to the yield stress times the value of the plastic modulus called as Z. And the plastic modulus for the rectangular cross sections is given as ZBD square by 4. The shear factor that we used in the design is generally is the ratio of the plastic moment and the yielding moment. That is the ratio of MP by My is called as the shape factor. And if we put on the numerical value of MP as was Z times Z, and the value of the yielding moment as yielding stress times stress in the structure, it ultimately becomes equal to the Z by S. So this ratio of section modulus is called as the shape factor, and its value comes out to be for rectangular sections is 1.5, because we have seen the value of the modulus or the plastic modulus, that is Z, its value is BD squared by 4, while the value of the section modulus for the rectangular members is BD squared by 6. And once we simplify this value, 6 by 4 comes out to be 1.5. But what is this shape factor? This shape factor is defined in the numeric terms, and it defined as the ratio of the plastic moment to the yielding moment. And as I already told you that for rectangular sections, its value is 1.5 and could vary from 1.1 to 1.2 for any standard roll beam sections. Well, the plastic modulus is defined as the ratio of the plastic moment to the yield stress of a member. It can We can also define it as the first moment of inertia about the neutral axis when the area above the neutral and area above and below the neutral axis are the equal. And the first moment of inertia about the neutral axis is basically the centroid of the axis. So this value of the plastic modulus, which is Z, is equal to the MP, which is the plastic moment divided by the yield stress. And this is derived from the definition of the plastic moment. Now coming towards the design of the steel beams, well, the development of the plastic stress distribution over the section causes two different length effects on the steel beams. First one, they causes the lateral torsional buckling, and it is developed before the section reaches the ultimate or the plastic moment stage. Second, the causes is the local buckling. Local buckling is basically the failure of the individual plates either in the flanges or in the webs of the section. And this failure is also developed before the compressive yielding stress is reached. So the two types of failure that would be noted is the lateral torsional buckling and the local buckling. And we must resist these two type of failures in during the designing stage of the steel beams. So the lateral torsional buckling, if we consider the simply supported beam, and once we subject the simply supported beam to a transverse loading in the gravity direction, due to this direction or due to this loading, the beam is going to deflect downward, and its upper part ultimately will be in compression, and hence upper part is going to act as the compression member, while below part is going to act as the neutral axis as the tension member, right? So this leads to the fact that we are going to use a beam as a compression member, while beams are generally used as a tension member. But this is occurred due to this lateral torsional buckling in the member. As far as the local buckling is concerned, for establishing the width to thickness ratio that limits the local buckling, the LRFD method specify the three distinct classifications for the local buckling prevention. First one is the we could have a compact section and it's have own formulas and its own theories. Second, we could have a non-compact section, and then we could have a cylinder section. So coming towards the compaction or the compact section, if the slenderness ratio, that is the ratio of width to thickness of the plate or the beam element, is the less than the lambda p, that is the plastic lambda, then the element is said to be compact, and it will only going to be fail or going to buckle after reaching the yield stress. So if we have the value of MP on the value of the MR, which is the resisting moment, and the value of the MP, which is the plastic moment, when the value of the MP is less than the value of the resisting moment, then the section is going to be compact. And for the non-compact sections, if the slenderness ratio of the element is less than the lambda r but is greater than the lambda p, then the section is called as non-compact, and it will going to buckle locally immediately after reaching the yield stress. So if the value of the lambda r is more than the less than the lambda r, but the value of the lambda p is more, the slenderness ratio or inductive slenderness ratio lies in this second column, then it is called as non-compact section. And if the slenderness ratio of the member or the plate is greater than the lambda r, then it is called as the slender member, and this will going to buckle in the elastic range even before reaching the yield stress. So we have the three different sections. First one is the compact section, in which the failure occur much after the yield point of the structure. And then we have a non-compact element, so the non-compact section in which the failure occur immediately when the value of the yield stress is reached. And third one is the cylinder element, in which we have the failure even before the value of the ultimate stress is achieved. So we have to prevent these type of failure by checking that whether beam is going to fail in the compact section, non-compact section, or the cylinder section, and then we are going to design accordingly on the basis of the loading. So a compact section that can develop fully plastic movement before local buckling, and compact section they generally develop the full plastic movement before the buckling starts. While the non-buckling is concerned, they are called for the non-compact sections are the sections that develop a movement equal to or greater than the yielding moment. But this value is less than the value of the plastic movement before the local buckling of any elements initiates. Then we have a cylinder sections in which if any plate element is cylinder, then we consider that the entire section is considered as the cylinder section. Now, coming towards the design part of the steel beams, as you have understood all the terminologies and the theories involved in the design part of the steel beams, let's have an example problem where we were supposed to select the light test W sections to carry a uniformly distributed load of 0.2 kg per foot, and this load is superimposed, which means that this load is additional to the self weight of the beam and also carrying a live load of 0.8 kg per foot. Simply supported span length is given as 20 feet. The compression flange is fully supported against lateral movement. So there is no going to be a lateral movement in the member. And we are supposed to use the LRFD method, and we are going to select the sections using the following steels. First is the A36 steel, then choosing A572 grade 50 steel, and the third one is 572 grade 65 steel. So basically this is a problem in which we have to carry out the calculations for three different types of the steel. So it will become as the problem of 3 in 1. Well, to start with, the very first step in case of the designing is the calculation of the ultimate load, and for that we have to write down the given data, as we are given with the dead load of 0.2 k feet, live load of 0.8 foot k, span length of 20 feet. If we proceed with the solution, first of all we are going to find out the factored load. So the factored load for the LRFT is going to be the 1.2 times of the dead load plus 1.6 times of the live load. Once we put in the values of the dead load and the live load, the results comes out to be 1.52 kips per foot. And if we find out the ultimate moments for uniformly distributed load, it's WL square by 8. And once we put in the value of this W of the load that is calculated in the previous steps multiplied with the length square of the span length, we find out that the moment comes out to be 76 feet kips. Now, let's start with the first steel, that is A36 steel. For during the designing stage, we already start by assuming that our section is compact in the nature, or indirectly we always first of all check that whether our section is compact or not. Then we are moved towards the non-compact section, and later on we will move towards the slender sections. We select this compact section because the major or the most all of the steel sections that are either cold rolled or hot rolled satisfies the condition of the compact sections for both flanges and for the webs. So if we find out the design strength of the member is, which is nominal moment or ultimate moment, and it's equal to 5b times sectional modulus time yield stress. Plastic modulus time yield stress. So in this case, we put in the values of mu as 5 mn It will going to we are going to find out the values of this value of zx, which is the plastic modulus, and will become as mu times phi b over fy. The mu that we calculated in the previous steps is 76 feet cubes, and we multiplied with L, converted into inches, divided by the phi b, that is the factors for beams, or the tension factors for tension members is zero point 0.9, multiplied with the yield stress of air 3060, which is 36 ksm. We got to know that the value of the section modulus comes out to be 28.1 inch cube. After this value of the z section modulus, we are going to move towards the LRFD manual. And if we move towards these LRFD manuals, you will see that the chapter 4 or LRFD manual is related to the beam and girder design. And in the chapter 4, you are given with the values of the table having the values of this plastic modulus zx, and it's mentioned that the for shape used as the beam, value phi of b is given as zero point 0.9. What you are going to do is you are going to find out the value of the zx that will be developed in the find out using the equations in the last step, and the value that we find out is 28.1. So we are going to find out the value of the zx, which is just above the 28.1, as we are given with the number of the pages of these tables, and they are decreasing with the increase in the number of the pages. So the value of the section modulus for 28.1, or the just above 28.1, that we obtain is 29.3 in this case. And because the smaller value is 27.2, and above that is 29.3. And the shape of this value section against this plastic modulus is W12 by 22. So you are going to write down this section and its plastic modulus in the next step. So we can say that from the LRFD manual, we are going to try the W12 by 22, W12 by 22, which is the section or the shape of the section having a modulus of 29.3 inch cube, which is just above the value of the 28.1 inch cube. So once you have the value, or once you noted down this section, that is W12 by 322, we are going move back to the chapter 1 of this LRFD manual, which is related to the properties of section modulus of different sections. So if we move towards this part 1, where we have a different sections and their dimensional properties. So the section that we are going to looking for is W12 by 22, W14, W12 by 336. Yeah, this is the section that we find out the W12 by 22. So we are going to note down the values that corresponds to this sections. While if you know that below it is written as 19, it means that the section is W12 by 19 and W12 by 16 and so on. And once you see the properties of this particular section or the any section, you will find the properties on 2 pages for a one section. Like we have mentioned a section as W12 by 22. In the very next page, it is again mentioned as the nominal weight of the section. And and the weight of the section is W12 by 20. So the weight of the section is 22. So we are going to write the values of these two, note down the values of these two pages. And if you move on to the second page, on the top it's written as the compact section criteria. And under the compact section criteria, we are given with the values of BF to TF, which is related to the criteria of the flanges. And other is given as the value of H by TW, which is the criteria for the web or for the compactness of the webs. So we are going to note down these two values. That the value for the BF by 2TF is 4.7 and the value of H by TW is 41.8. You can substitute use this value directly, or you can find out the value of B by 2 TF also as well. That in the first page you are given with the flange width and the thickness as well, and similarly you are given with the value of the web thickness as well. So you can use these values as well, or you can directly use the values given on the second page of this AISC manual for section W12 by 22. So once we have noted down these values, we have the formula for flanges. For the compactness of the flanges is BF by 2TF, and its value that we noted from the table comes out to be 4.7. And if you use the formula, it also comes out to be the same. And the value of the lambda p, which is the plastic moment, the criteria against which we are going to check the compactness of the member is 65 divided by radical of yield stress, and it comes out to be 10.8. As the weight criteria for the compactness is that the value of the lambda should be less than the lambda p, and this criteria is satisfying in this case, so the flange compactness is okay. Then we are going to check the compactness of the webs, and for the web we have the formula of lambda is equal to H by TW. So for that we take noted from the table that the compact sectional HC by TW is equal to 41.8, and the formula for the lambda P for webs is 640 by the root 1, and it comes out to be 10.7. This criteria is again satisfying, so our both criteria are satisfied. Once the criteria are satisfied, we are going to check out the strength of the section that we have selected, that is W12 by 22, which is we are drawing in this problems, that whether this section sustain the loadings that the loading is applied on the structure. For this strength check, we are going to again find out the factored moment of that generated due to load. But this time we are going to include the weight of the beam as well, because we know we have a section, or we have selected the section of the beam. So in this case, the total dead load now becomes as 0.2, which is a superimposed dead load plus 0.022, because the 22 pound per foot is the weight or the load, the dead load or the self weight of the member W12 by 22. So it's added up and it comes out with resultant total dead load becomes as 0.222 kg per foot, and the drive load remains the same. We are going to use the same expression for the ultimate load, that is 1.2 times dead load plus 1.6 times live load, and we are going to find out the value of the ultimate moment using the expression WL square by 8, and this value comes out to be 77.5 kps fit. Now, if we find out the value of the plastic moment, which is equal to Zx by Fy, Zx is the plastic modulus, and the for section W12 by 22, its value is 29.3. It's multiplied with yield stress of the K36 steel, which is 36 KSI, and we divided it with that 12 to convert it into fits. Now its value comes out to be 87.9 kips. And once we multiply this 87.9 with the factor of safety, which is zero point 0.9, its value comes out to be 71.1 kip fit, which is more than the value of the ultimate load or the moment that is acting due to generated or acting due to the load, which is 77.5. So our section is okay because the moment that is generated due to loading is 77.5 kp, while our section can register movement of 79.1 kips. So we can say that the final solution for A36 steel is W12 by 22 with Fy of 36 KSI. And the second problem we are given, or the second part we are given with the A572 grade 50 steel, and for that we are going to repeat the same procedure that we did for A36 steel. That first of all we are going to find out the values of the section modulus, which comes out to be 20.3. Then we are going towards the manual and selecting for a section whose values is greater than or the equal to this value of 20.3. From there it comes out to be 12 by 16. And then we are going to apply the compact section checks by looking the values of the compact section criteria from chapter 1 of the AIC manuals, the values of the BF by 2TF and the values of H by 2TF. And again, both criteria are satisfied using this problem as well, and then we are going to check out the strength check for this member as well. And the strength criteria for this member is again repeated in the same manner, and the self weight of the member will again going to be added in the load of the dead load of the structure, and it's ultimately going to satisfy the moment or the load carrying capacity of the structure as well. Like what, then let's move towards the third problem, which is A572 grade 65 steel. And for that we are again moving towards the same step that we are first of all we are going to find out the values of the ZX, which is section plastic modulus, and it comes out to be 15.6 inch cube. And we're going to find out the sections that is matching with this section modulus is W12 by 14. And once we find out the values of the compactness for flanges in this section, it comes out to be 8.8. While once we apply the formula or the limiting criteria of lambda p for flanges, its value comes out to be 8.06, which means that the value of the lambda is more than lambda of p, but instead of the less than the lambda of p. So this is not the governing criteria or not the governing section for compactness. But we are going to check whether this section is not compact only in flanges or in case of webs as well. So once we apply the formula for the web, it is going to satisfy the conditions. So we can say that the controlling limit state for this particular problem or for this particular part of the question is the local buckling failure in the flanges. So this section will be termed as non-compact in for flanges. And for non-compact sections, we are going to check the strength of the structure by interpolating the values between the plastic moment and the yield moment. So the values that comes up after interpolation, it will become as mn, the nominal moment, equal to minus mp minus mr multiplied with lambda minus lambda p over lambda r minus lambda p. where the value of the lambda r is equal to 141 over under root fy minus 10 as given in the AISC manuals chapter 4 of AISC. And this lambda r value comes out to be 19 after the substitution of the values. Now for non-compact section, the values of this interpolated value of Mn should be less than the value of the plastic mode. For that, we have to check the values of the plastic moment and the nominal moment first. So the plastic moment is equal to the plastic modulus times yield stress, and the plastic modulus for this is comes out 17.4. When it's multiplied with 65 divided by 12, it comes out to be 94.2 kPa. Similarly, the value of the MR or the resisting moments is equal to the sectional modulus Sx times Fy minus Fr. So it will become as 14.9, the sectional modulus for this particular section that is selected previously, and times multiply with 65 minus 10, which is the value of the Fr, that is the resisting force. It comes out to be 68.3 kips fit. And once we put this value into the equation of the nominal moment, the resultant moment comes out to be 92.5 kip fit. After that, we are going to apply the strength check using the same procedure, that adding the load into the structure, dead load of the structure, finding out the ultimate moment, and multiplying with factor of the safety to find out the values of the demand and the required moment. So in this case, the ultimate moments comes out to be, due to loading, comes out to 77 kips, while the ultimate moment or the load carrying capacity of the structures comes out to 83.25 kip fit. So we can say that we are going to select a section W12 by 16 with Fy of 65 KSI, because this is the section that we basically selected on the basis of the sectional modulus. Their previous states on the basis of section modulus. So with this, I would end our today's class. If you have any doubt, you are more than welcome to ask at any time. Thank you. Allah Hafiz.